June 2nd, 2015. Quick astronomy talk. With astronomy, I've learned that they had biases towards Big Bang. All the scientists looked up at the sky and said, well, we think the Big Bang happened, so anything that they see up there was immediately evidence for what they already believe. They had a cognitive bias. And that cognitive bias I'm learning, being that I'm reading about these semiconductors and diodes and things like that, was that when they looked through their horn, Penzias and Wilson looked through the horn at the night sky, they noticed that there was microwaves coming from all directions. Now, how could that be? Where are microwaves coming from? And boom, they automatically assumed that it was evidence for the afterglow of some Big Bang event, which then made them branch off into some Big Bang creationist world where all astronomers believe that the Big Bang happened. And then, instead of, going in terms of, oh, maybe it's an electrical process, maybe it has something to do with electrical activity in outer space. Instead of doing that, they branched off. So what happened is the electrical engineers went this way, and the Big Bang people went this way. And now we're stuck with people thinking that dark matter and dark energy are real things and all this other nonsense, and aging stars based off of weird metallicity rules and all this other stuff. And then you have electrical engineers only focusing on industrial things where they deal with transistor manufacturing, diode manufacturing, electrical component manufacturing, and their entire thing is all, circled around manufacturing. And then you have these people looking through the telescopes that are like, well, the Big Bang happened. Do you see like the big difference here? That it's two completely different mindsets altogether. But what needed to happen was some of those electrical people needed to go over to astronomy and say, hey, the microwave background radiation isn't some afterglow of some random Big Bang event. It's just signaling electrical activity in outer space. We need to explain it in terms of what's going on there in electrical terms and interpretations. So basically that branching off, I think, happened in the 1950s and 1960s. So now we're stuck with Big Bang stuff, and we're just waiting for it to eventually disintegrate, which will happen over the next 20 years. But unfortunately, what's happened now is that we have this weird mythology group called Electric Universe that's trying to hijack the electrical interpretations, and then they're trying to justify everything inside of the Worlds in Collision book written by Velikovsky. So it's the same crap the Big Bang people pulled in the 1950s and 60s, only they're trying to make everything justify the Velikovsky nonsense. So they're going to branch off, and mind you, it's not going to be as big as a branch as the astronomers did in the 1950s and 60s, but it is going to have parallels to that. But I think just tossing mythology and Velikovsky in the trash can is the best idea. On another note, phase transition. I have my laptop here. I'm going to go ahead and read this out to you. A phase transition is a transformation of a thermodynamic system from one phase of state of matter to another by heat transfer. The term is mostly commonly used to describe transitions between solid, liquid, and gaseous states of matter, and in rare cases, plasma. Now I want you to notice that. They say, in rare cases, there are plasma phase transitions. What about lightning? Is that rare? No. What about stars, young stars like the sun, that are radiating massive amounts of heat, and the plasma is recombining into gas, releasing massive amounts of heat? meaning every single star in the galaxy that is young like the sun, as well as all young stars in every single galaxy across the universe, are engaging in plasma recombination. So where is this rare nonsense coming from? It's not rare at all. But that's the attitude that a lot of these people have that want to place plasma into its little, oh, this is too strange, we don't understand this, into the little box, and just to ignore it. As well, the phase transition diagram, where it goes over critical point and triple point, it can include not superfluid, I think super liquid, I can't remember what that word is, but basically it's a state of matter between gaseous and liquid material where there's enough pressure and heat to keep it at that temperature. Now, there was a phase transition that I noticed because the solid portion of the graph interacted with that super fluid. Hang on, I wrote it down somewhere. Hang on. Supercritical. That's it. Supercritical phase transition, where the heat and the pressure is high enough to keep it at some distinct, not gaseous, not liquid phase of matter. And on the phase diagram, I think I'll go ahead and do a review on it on the whiteboard later today. But the phase diagram had solids touching liquids on this side, and then it had the supercritical touching the liquids, and then, you know, obviously it had the gaseous matter down here. So it's touching liquid and gaseous matter, which was supercritical right here. And then you had solids reaching all the way up where it could be highly pressurized and touching the supercritical matter as well. But even with those, including supercritical matter, which was the strange form of matter in this regard, there's no mention of plasma. There's no place for plasma on this phase diagram, which is really strange because plasma is a distinct phase of matter. So what I'm going to do is go ahead and try to make one of those diagrams, including supercritical, including a type of phase transition where it actually phase transitions, it just doesn't undergo effusion. More talk on that later. But that it doesn't just effuse into the solid material, but that it's a distinct phase of matter. And I want to go over what would happen if plasma transitioned to supercritical matter. And that's a very weird phase transition in itself. I don't know, I was just reviewing it yesterday, and I think there needs to be some kind of talk about it, if it's possible, and what that matter would actually look like and how it would interact. But that, and I'm overviewing this book still, basically on it says Physics Demystified. Now, I know it was written in 2002 or copyrighted in 2002, but I think one of the important things that people should learn about is semiconductors, where it has N and P type material. You can learn how some diagrams, circuitry are written out. You can learn about different kinds of diodes, photovoltaic cells, LEDs, tunnel diodes, what rectification is, what detection is, what an avalanche is, what gun diodes are. Those are confusing to me. I have to research those a little bit more. But basically you have different kinds of current amplification with semiconductors. And that's very interesting because semiconductor material is silicon. Silicon can be doped on both sides to make an N and P type junction, or NP junction, I guess that's what you would call it. But the fact that Earth has an enormous amount of silicon in its crust is kind of strange. And I know I talked about this earlier, but to think that maybe the semiconducting properties of silicon have a large role in the fact that it was one of the last solid material to deposit onto the crust. There's something to do with that. I don't know. There's a discovery to be made somewhere in there, but I'm not too sure what it is. But anyways, I think I made this talk long enough. Alright, later.